Good afternoon, ladies and gentlemen. I'm Haydar Haydar. My friends are Muhammad Imrad and Marwa Mahdarani, and we are looking forward to talking with you about the computer processing of a human language. But before I start, do you know why the PowerPoint presentation crossed the road? It's to get to the other slides and let it slide. Today I will be discussing with you the computer processing of a human language, giving you some background information. Moreover, I'll discuss the computational semantics and computational pragmatics, while Muhammad Ibrad will be presenting with you the computational phonetics and phonology, text-to-speech, computational morphology, and computational syntax. And Marwa will go over the rest. To begin with, computational linguistics is an interdisciplinary field concerned with the statistical or rule-based modeling of natural language from a computational perspective. The prime aim of computational linguistics is to create software or computer systems that understand and speak any human language. Moreover, computational linguistics include the analysis of written texts and spoken discourse, the translation of text and speech from one language into another, the use of a human language for communication between computers and people, and the modeling and testing of linguistic theories. It's also concerned with how computational methods can aid the understanding of a human language. All in all, there is a number of definitions of the term computational linguistics, and here are some of the terms related to computational linguistics, such as computer science, psychology, language and linguistics, artificial intelligence, physiology, logic, and HCI. Here, HCI stands for human computer interaction, which enables the user to communicate with the computer or any other electronic device through a certain language. Okay, the following tree diagram shows the different branches and levels of computational linguistics in tune with the study of languages. Computational linguistics has two main parts or components, which are the theoretical computational linguistics and the applied computational linguistics. First of all, the theoretical computational linguistics takes up issues in the theoretical linguistic and cognitive science. It deals with formal theories about the linguistic knowledge that a human need for generating and understanding language. The essential components of language or the building blocks are sounds, words, sentences, and meanings. All these elements are equally important. They give rise to understanding the building blocks of language at different levels of structure. Like phonology, morphology, semantics, syntax, and discourse. On the other hand, the applied computational linguistics focuses on the practical outcome of modeling human language use. The methods, techniques, tools, and the applications used in the applied area is also termed as the human language engineering or the human language technology. The applied computational linguistics is now widely used in language studies, business and scientific research, and development domains for many purposes. Okay, I'll go for the other slides. Okay, computational semantics is the representation of the meanings of words and morphemes in the computer, as well as the meanings derived from their combinations. It has two main concerns. One is to produce a semantic representation of language input, and the other is to take a semantic representation and produce a new natural language output that conveys the meaning. For example, let's take a look at the circuit fixed chop, which is a question answering system designed to help a technician repair a faulty circuit. When in operation, the system The system fixed shop must create a semantic representation, act on it, and produce another semantic representation, which it then outputs to the user in ordinary language. When the technician says that I need to fix the RS111 circuit, the system recognizes that I means the user, that needs to represent something that the user lacks and the computer must provide. It further knows that if fixing is what is needed, then it has to provide information about the workings of something. It recognizes that the RS111 circuit as a circuit with certain properties that are contained in its semantic representation. The system infers that the workings of that particular circuit will be central to ensuring dialogue. Therefore, to generate sentences, the computer tries to find words that fit the concepts incorporated into its semantic representation. Then the computer must decide what to talk about next, like the user, the light, the wire, or whatever. To achieve speech understanding, the computer needs to choose words corresponding to whether to describe the state of an object in its peer view, ask about the state of an object in the user's peer view, make a request of the user, tell the user what to do next, and so forth. A computer can represent concepts in many ways, but all share one unity, which is a lexicon that contains morphological, syntactic, semantic, and thematic information that depend on the particular applications it is to be suited for. Furthermore, the use of networks that concern words to their semantic role is one of the schemes for semantic representation that have been developed by computational linguists. For example, let's take a look at this sentence. You put up the switch. Here, the user, you, is the agent or doer, and put up is what to be done, and it's to be done to the theme, which is the switch. And now, let's watch this short video about Google Translate.
Google Translate is a free tool that enables you to translate sentences, documents, and even whole websites instantly. But how exactly does it work? While it may seem like we have a room full of bilingual elves working for us, in fact, all of our translations come from computers. These computers use a process called statistical machine translation, which is just a fancy way to say that our computers generate translations based on patterns found in large amounts of text. But let's take a step back. If you want to teach someone a new language, you might start by teaching them vocabulary words and grammatical rules that explain how to construct sentences. A computer can learn a foreign language the same way, by referring to vocabulary and a set of rules. But languages are complicated, and as any language learner can tell you, there are exceptions to almost any rule. When you try to capture all of these exceptions, and exceptions to the exceptions, in a computer program, the translation quality begins to break down. Google Translate takes a different approach. Instead of trying to teach our computers all the rules of a language, we'll let our computers discover the rules for themselves. They do this by analyzing millions and millions of documents that have already been translated by human translators. These translated texts come from books, organizations like the UN, and websites from all around the world. Our computers scan these texts looking for statistically significant patterns. That is to say, patterns between the translation and the original text that are unlikely to occur by chance. Once the computer finds a pattern, it can use this pattern to translate similar text in the future. When you repeat this process billions of times, you end up with billions of patterns and one very smart computer program.
Yeah.
For some languages, however, we have fewer translated documents available, and therefore fewer patterns that our software has detected. This is why our translation quality will vary by language and language pair. We know our translations aren't always perfect, but by constantly providing new translated text, we can make our computers smarter and our translations better. So next time you translate a sentence or web page with Google Translate, think about those millions of documents and billions of patterns that ultimately led to your translation. And all of it happening in the blink of an eye. Pretty cool, isn't it? Give it a try at translate.google.com.
Okay, last but not least, computational pragmatics is the interaction of the real world with the language system. Computational pragmatics may influence the response of the computer by taking into account knowledge that the computer system has about the real world. For example, that there is a unique element in the environment, so the determiner that can be used appropriately to refer to it. When a sentence is structurally ambiguous, such as he saw the boy with the bicycle, then the parser will compute each structure. However, semantic processing may eliminate some of the structures if they are unusual. In this case, the bicycle is not a tool for viewing objects. Then one parse can be rolled out. And finally, knowledge is needed to determine the intended meaning or when two expressions refer to the same object. And that's all. That's a minute. Hope you enjoy your time. Thank you for listening. Keep safe and stay at home.